Okay.
1 second. Is it displayed correctly?
Yes, we can see your screen, but the one with the presentation, not in present, not in, yeah. It's just showing the PowerPoint.
Sorry, then I will adjust. Somehow my docking station is giving me a hard time. It's glitching. Right, and now it's supposed to be the full screen, right?
Yes, very nicely. Thank you.
Hello everyone. My name is Abdulrahman Nahhas. I work for the Ottoman Turk University in Magdeburg, and I will be talking today, presenting our hybrid design that we applied for solving hybrid closure scheduling problem with family setup times. Shortly, the content of the outline of this presentation structure as follows. So we start with an introduction. Then I will elaborate a little bit about scheduling problems, but not in details because we have already heard multiple talks talking about scheduling problems. Then I will explain more about how we combine different heuristics and meta-heuristics approaches for approaching that problem. And then I will give an overview of the computational results before closing this presentation with conclusion for the research directions. The problem on hand is motivated by an industrial use case study in the field of printed circuit board assembly. Such production systems are known to be extremely heterogeneous with many requirements, where also, as we've seen in the previous presentation, delivery date or so-called tardiness as an objective function is very important performance literacy. In addition to quality of productions, plus, of course, as any other manufacturing enterprise course, it's always an indicator or performance indicators that want to be minimized. So the problem on hand is formulated to be solved addressing multi-objective optimization measures to address machine utilizations and violations in delivery date, which is more dedicated to customer satisfaction. In general, scheduling problems are known to be very complicated. Despite their operative nature, they have a very, very critical impact on the overall performance of an enterprise. If we want to roughly classify solution techniques that can be found addressing the hybrid closure scheduling problems, they can be divided into two main research streams: exact and analytical methods, such as branch out, dynamic programming, and many others, or heuristic solution techniques, under which falls constructive approaches of priority dispatching rules, improvement, and meta-heuristic approaches such as evolutionary algorithms, simulated annealing, and many others. The presentation is not moving, isn't it? Oh, I'm sorry. Is my presentation moving now?
Now it is moving.
No, I'm very sorry. Okay. Here's the content of the outline. Here's the motivation and introduction.
It's no problem. We listened, so I think everybody got it until now. So now we see the slides. Thank you.
Okay. And here is the often used solution methodology. And here we go, scheduling problems in general. And now I will elaborate more on the investigative production system. The problem that investigated involved 4 production processes or production stages. On every stage, exist multiple machines that are parallel. They are not identical. They are of different speeds. However, they all can process all jobs of the same nature. And I don't want to go through the specificity of the of every production process. Very roughly, the entire production process starts by a surface mounting device in which those small parts are placed on the printed circuit boards. Then followed that process comes an automated optical inspection. That's the second production stage, and then selectively there are some jobs that undergo the third stage, which was selective soldering, and or the fourth stage. So not all jobs follow the third and the fourth stages. Exactly. This implementation is actually part of a larger framework, and it's actually the adaptive scheduling component that we developed. The entire design consists of two main elements. First, the optimization model, which is based in this presented approach on combining evolutionary algorithms and sorting dominated genetic algorithms with a set of developed, self-developed heuristic techniques and normal priority dispatching rules. For evaluation purposes, we developed a simulation model, which serves as an evaluation component. And as the majority of evolutionary algorithms or meta-heuristic techniques, we start our optimization with a set of individuals that constitute our population, and after the randomized or the initial population is generated, we start evaluating every solution instance to assign different fitness values for every objective values for our solution individuals. And then at some point, once we evaluate all individuals, we go through the evolutionary process, such as the selection process, the mutation, and the crossover, before repeating the same process again, and we keep doing that until some breakpoint criteria is met. Just to give an impression about the complexity of the problems, we have problem instances. We have over 200 problem instances that are extracted from the ERP system of the enterprise. Here I will give elaboration on the comparison that we conducted to previous works. So first, we wanted to achieve sort of comparison to what already exists in the literature and see if we are achieving any enhancement. And that's why we conducted experiments on a two-stage problem instances, compared them to one of the published work in the literature, and then showed how that will work also in four-stage problem instances, and then conducted further experiment on the rest of the problems. It will be too hard to talk about all of them, but I will try to give an overview, short overview on an impression on how the performance looked like. We are talking about problems that involves between 150 and 170 jobs per problem instance, and they belong to up to 40 different families. And when we switch between families, once we schedule jobs, we always have an induced major setup times that is actually just pause time, which we aim to minimize. Exactly. And here comes to the design. We relied on the NSG-A3 as a control strategy to design our solution technique. And we encoded a multi-population solution, in which we said, okay, the first population will be responsible for selecting different allocation algorithms over time. And the second population is a binary decision points, in which I would decide, or the control strategy in the sense we decide, whether we need to reallocate or to reschedule our jobs during the simulation or not. And the third population is encoded to give a selection of the appropriate sequencing algorithms. So we have set of sequencing algorithms, set of allocation algorithms, and set of binary decision points. And all those three populations are shuffled over time and manipulated during the simulation to find best or to find very high quality solutions. Now, to evaluate that dynamic, we relied on discrete event simulation engines. We built a simulation model, which is based on Python, that has, of course, access, which is to different those set of allocation and sequencing algorithms. And I think I will elaborate more based on those questions. And I will discuss directly the computational results. Now, the experiments are all conducted on a normal, actually not on a laptop with 16 cores. And 64 gigabyte RAM. The computational results of the experiments to minimize the maximum completion times and the major setup times, which are more designed to increase machine utilization and to minimize the total tardiness and penalties for customer satisfaction. So we have 4 objective values. But in these figures or in these tables, I will be discussing only 2 objective values because the other 2 objective values are minimized to the level of 0. So I just didn't want to put them because it doesn't make sense here in this sense. In comparison to related literature, as the published work in 1, we compared our techniques to the so-called NEAT, which is neural network-based solution, taboo search and simulated annealing. And we can see that in terms of minimizing the max spans, we are marginally outperforming both meta-heuristics and very close to NEAT, while in terms of minimizing major setup times, the difference in comparison to NEAT is significant, while taboo search and simulated annealing report better results. And now here I have to say that both SA and the simulated annealing and taboo search were set to run based on weighted sum, which might explain why, for example, major setup time in this sense was favored against Cmax. And in our implementation, we favor all objective values and specifically the max span at the beginning. We see a very similar performance for problem 2, while actually in problem 2, we dominate all solution techniques. Problem 3 the same, and problem 4 as well the same. But however, we do not report really significant outperformance in terms of the max span. Now going forward to the computational results of the 4-stage problem instances, a very similar tendency can be seen. For minimizing the max spans, we more or less achieve the best results in comparison to the hybrid GA, ESPO, and earliest due date, which are some simple heuristics and priority dispatching rules, against hybrid genetic algorithms based on weighted sum. I think there is only in problem 6, the hybrid GA would outperform minimally our suggested solution here in terms of minimizing the max span. So yeah, now to take a look into how a 2-dimensional presentation of these objective values look like for the 4-stage problem, that's just an exemplary representation. You see here that for minimizing the max span against average tardiness, right at the bottom left of the first figure A, how our best solution individuals are identified, while if I would plot major setup times against the max span, I would see more, I would notice more conflicting nature of the objective values, since I see some of the best solutions or non-dominated solutions right in the middle. And if I would plot the average tardiness against major setup times, I see a complete complete conflicting natures of objective values. And that's what make it, I wanted to point out how complicated it can be if I want to pursue a multi-objective optimization problems, and how the conflicting natures of those objective values might impact significantly the best identified solutions in this sense. Now, that's a 3D presentations of all objective values. So down at the bottom, we have the max span minimization, while on the left, we have the major setup times and the average tardiness. And we see that the best solutions are identified on the outer side of all individuals that are inside. And the best solution is right down at the end, in which the average tardiness is 0. So we do not want violations in the delivery date. So we want to minimize the total tardiness, but take into account that our efficiency has to be taken into account through minimization of the max span, the number of major setup times. And this is the results, well, when we compare it to known published work in the literature. Let's take a look into how that performed for solving, let's say, 30, 40 problem instances. So I selected 30 problem instances for minimizing the max span. You see here, for example, I will try not to bore you with the details of numbers. Here, the comparison is between the hybrid approach, the genetic algorithm, just simple meta-heuristic, against one priority dispatching rules, the earliest due date, which is designed to minimize the total tardiness. And you see here that if we compare between in percent, we are able to achieve up to 25% better performance in comparison to GA, and that comparison is really against the GA, the genetic algorithms, because we outperform and report full dominance for solving 28 problem instances, while still getting outperformed by genetic algorithms for solving 2 problem instances. Now let's take a look into number of major setup times, how that looked like. And we have similar tendency. However, the increase of performance, or the increase in the performance, is quite less than the max span, but it's the same. It shows us the same tendency. You see here that the genetic algorithms still outperform for solving minimally for solving 5 problem instances, while the multi-objective hybrid technique can outperform all other techniques for solving the other 26 problem instances with an outperformance that reach up to 15%. I think I came to the conclusion of this talk. I mean, the average required computational effort by the hybrid approach for solving the problem instances was an average around 5 minutes, where pure GA would require an average 50 minutes for solving the problems. The presented approach reports complete dominance in terms of minimizing all objective values for solving 23 problem instances, if we recap the 2-stage, the 4-stage, and the further experiments. And the framework reported a max span 93% to considered problem instances. Obviously, priority dispatching tools fails to report even acceptable results for minimizing neither the max span nor the total number of major setup times, while we see, of course, because it's designed to minimize the total tardiness, it does report good results on the total tardiness. And we still need to conduct further analysis to investigate further the robustness of the technique. And we still in the process of designing the mass experiments to see how the performance look like on the rest of the problem instances. And by that, I want to thank you for your attention, and I will be very happy to answer your questions.